In the present video, we will solve the example problem of big M method. Let's see the problem. Minimize z equal to 5x1 plus 3x2 subject to the constraints 2x1 plus 4x2 less than or equal to 12, 2x1 plus 2x2 equal to the 10, 5x1 plus 2x2 greater than or equal to 10 and x1 comma x2 greater than or equal to the 0. Let's see the solution. Here objective function is minimization model. So first we have to convert the minimization model into the maximization model by multiplying with the -1. Then objective function is maximize z equal to minus 5x1 minus 3x2. Next step is convert general linear programming problem into standard linear programming problem. In this regard, we have to add the slack variable s1 which is greater than or equal to the 0 in the first constraint. Then first constraint will become the 2x1 plus 4x2 plus s1 equal to 12. Next to add artificial variable a1 which is greater than or equal to the 0 in second constraint. Then second constraint will become the 2x1 plus 2x2 plus a1 equal to the 10. So next we have to add the surplus variable s2 and artificial variable a2 which is greater than or equal to the 0 in the third constraint. Then third constraint will become the 5x1 plus 2x2 minus s2 plus a2 equal to the 10. So next we have to rewrite the objective function in the terms of decision variables, slack variables, surplus variable and artificial variables. And moreover, cost coefficient for the slack and surplus variable is 0 and for the artificial variables cost coefficient is the minus m. Then objective function will become the maximize z equal to minus 5x1 minus 3x2 plus 0s1 plus 0s2 minus m-a1 minus m-a2 where x1, x2, s1, s2, a1, a2 all are the greater than or equal to the 0. Second step is find the initial basic feasible solution. For this we have to consider the decision variables and surplus variables are the 0. So here decision variables are the x1 and x2, surplus variable is the s2. So consider x1 equal to x2 equal to s2 equal to the 0 and substitute these values into the constraint. Then we will get the initial basic feasible solution. From the first constraint equation, s1 equal to the 12 and from the second constraint equation a1 equal to the 10 and from the third constraint equation a2 equal to the 10. So s1 equal to 12, a1 equal to the 10 and a2 equal to the 10. So third step is construct the initial simplex table. So this is the initial simplex table. Here B is the basis variables. Here basis variables are the S1, A1 and A2. So write down S1, A1, A2 in the B column. Next to CB represents the cost coefficients for the basis variables. For the S1 cost coefficient is the 0 and for the A1 cost coefficient is the minus m and for the A2 cost coefficient is the minus m. So write down the 0 minus m are the values in the CB column. Next to XB represents the initial basic feasible solution, that is S1 is the 12, A1 equal to the 10, A2 equal to the 10. So next to CJ is the cost coefficient value of the all the variables. In this regard, you have to observe the objective function and cost coefficient for the x1 variable is the minus 5, for the x2 minus 3, 0 for the s1 and s2, minus m for the a1 and a2. So Cj values are the minus 5, minus 3, 0, 0, minus m, minus m. So next to observe the constraint equations and write down the coefficient values of the all the variables. So from the first constraint equation, x1 coefficient is the 2. So write down the 2 here. And next for the x2 coefficient is the 4. Next for s1 coefficient is the 1. So here there is the no s2, a1 and a2. So its coefficients are the 0, 0, 0. Next we have to move to the second constraint equation. From the second constraint equation, so x1 coefficient is the 2, x2 coefficient is the 2, and there is no s1 and s2, so 0, 0, and a1 coefficient is the 1, there is no a2, so its coefficient is the 0. And next we have to go for the third constraint equation. Here x1 is the 5, x2 2, and there is no s1 0, and s2 coefficient is the -1, and there is no a1, so 0, and a2 coefficient is the 1. This is the initial simplex table. And next we have to go for the next step is calculate the values of Zj minus Cj and check the basic feasible solution for optimality. If all the Zj minus Cj is equal or greater than the 0, then optimal solution is obtained. If at least one Zj minus Cj value is the negative, then indicated by arrow, and respected column we are calling as the key column, then I have to go for the next iteration. If more than one Zj minus Cj is the negative value, then we have to choose the most negative of them, and this column we are calling as the key column. So first we have to go for the calculations of Zj minus Cj, which is equal to the summation of Cbj xj minus Cj. So first I have to go for the Zj minus Cj for the first variable, that is for x1 variable. So Z1 minus C1, which is equal to the Cb x1 minus C1, which is equal to the 0 into 2 plus minus m into 2 plus minus m into 5 minus of minus 5, which is equal to the minus 7m plus 5. So next for the x2 variable Z2 minus C2, which is equal to the 0 into 4 plus minus m into 2 plus minus m into 2 minus of minus 3, which is equal to the minus 4m plus 5. Next Z3 minus C3 for the third variable, that is for the S1 variable, which is equal to the 0 into 1 plus minus m into 0 plus minus m into 0 minus 0, which is equal to the 0. Next Z4 minus C4 for the fourth variable, S2 variable. So here 0 into 0 plus minus m into 0 plus minus m into minus 1 minus 0, which is equal to the m. Next to Z5 minus C5 for the A1 variable, which is equal to the 0 into 0 plus minus m into 1 plus minus m into 0 minus of minus m, which is equal to the 0. Similarly for the Z6 minus C6 for the sixth variable, that is for the A2 variable. So 0 into 0 plus minus m into 0 plus minus m into 1 and minus of minus m, which is equal to the 0. Here Z1 minus C1 value is the minus 7m plus 5 and Z2 minus C2 value is the minus 4m plus 5. These are the negative values. So among these two values, most negative value is the minus 7m plus 5 for the x1 variable. So I have to select the most negative value, that is minus 7m plus 5 for the x1 variable, and x1 column we are calling as the key column and it is calling as the incoming vector. So x1 variable is enters into the basis. Next step is calculate the minimum ratio, where minimum ratio equal to the xb divided by ck, where ck is represents the coefficients of the incoming variable. Here incoming variable is the x1. So first we have to determine the xb divided by ck for the first row, that is for the S1 variable row. So here xb value is the 12 and ck value is the 2. So 12 by 2, which is equal to the 6. Next for the second row, that is for the A1 variable row. So xb value is the 10 and ck value is the 2. Then 10 by 2, which is equal to the 5. And next for the third row, that is for the A2 variable row. So here xb is the 10 and ck is the 5. So 10 by 5, which is equal to the 2. So among these values 6, 5, 2, minimum ratio is the 2 and indicated by arrow. So A2 row, so A2 is outgoing vector and calling as this row is the key row. So here this third row, that is the A2 variable row, is the key row and A2 variable is the outgoing variable. So A2 variable, which is the leaves from the basis. So next we have to identify the common element in the key row as well as the key column. Here key row is the A2 variable row and the key column is the x1 variable column. Among these two, common element is the 5. So 5 is calling as the key element. And next step is construct the new simplex table by entering the incoming vector. Now we have to construct the new simplex table, that is first iteration. So here Z1 minus C1 value in X1 column is largest negative. So basic variable X1 is chosen to replace non-basic variable A2 in the basis. So here A2 is leaving variable from the basis and X1 variable is entering variable in the basis. So we have to remove the A2 column in the new simplex table. And moreover here R1 volt, R2 volt, R3 volt are the row 1, row 2, row 3 of the volt simplex table. R1 new, R2 new, R3 new are the row 1, row 2, row 3 of the new simplex table. So now we have to replace the X1 to the A2. So in the basis we have to write down the X1. So basis variables become the S1, A1, X1 and its CB values are the 0, minus M, minus 5. So next we have to apply the following row operations for the new simplex table. Remember, so before applying the row operations, in the key column, except the key element, remaining elements should be the 0 and key elements should be 1. So in the X1 column, so here this is the key element position. Here we have to get the value 1. Remaining element should be the 0. In this regard, we have to follow the row operations. So first row operation is the R3 new equal to R3 volt divided by 5. So R3 volt elements are the 10, 5, 2, 0, minus 1, 0. Divided by 5 means it will become the 10 by 5, 2, 5 by 5, 1, 2 by 5 and 0 by 5, 0, minus 1 by 5 and 0 by 5, which is equal to the 0. Next row operation is the R1 new equal to the R1 volt minus 2 R3 new. So first write down the R1 volt elements, that is the 12, 2, 4, 1, 0, 0. Next R3 new elements are the 2, 1, 2 by 5, 0, minus 1 by 5, 0. Then 2 R3 new is the 2 into 2, 4, 1 into 2, 2, 2 by 5 into 2, 4 by 5, 0 into 2, 0, minus 1 by 5 into 2, 2 by 5, 0 into 2, 0. So next we have to do the operation is R1 volt minus 2 R3 new, that is 12 minus 4 which is equal to the 8. 2 minus 2 0. 4 minus 4 by 5 which is the 16 by 5. 1 minus 0 1. 0 minus of minus 2 by 5 which is the 2 by 5. 0 minus 0 0. So enter these all the values in the R1 new row. Next row operation is the R2 new equal to R2 old minus 2 R3 new. So write down the R2 old elements, that is 10, 2, 2, 0, 0, 1. And R3 new values are the 2, 1, 2 by 5, 0, minus 1 by 5, 0. Then 2 into R3 new will become the 4, 2, 4 by 5, 0, minus 2 by 5, 0. Then R2 old minus 2 R3 new which is equal to the 10 minus 4 which is equal to the 6, and 2 minus 2 0, and 2 minus 4 by 5 6 by 5, 0 minus 0 0, 0 minus of minus 2 by 5 2 by 5, 1 minus 0 1. Enter these values in the R3 new row. So this is the new simplex table. Then once again you have to calculate the ZJ minus CJ values and check the basic feasible solution for the optimality. So Z1 minus C1 which is equal to the 0 into 0 plus minus m into 0 plus minus 5 into 1 minus of minus 5 which is equal to the 0. Next Z2 minus C2. So 0 into 16 by 5 plus minus m into 6 by 5 plus minus 5 into 2 by 5 minus of minus 3 which is equal to the minus 6m by 5 plus 1. Next to Z3 minus C3 which is equal to the 0 into 1 plus minus m into 0 plus minus 5 into 0 minus 0 which is equal to the 0. Next to Z4 minus C4, 0 into 2 by 5 plus minus m into 2 by 5 plus minus 5 into minus of 1 by 5 minus 0 which is equal to the minus 2m by 5. And next one is the Z5 minus C5 which is equal to the 0 into 0 plus minus m into 1 plus minus 5 into 0 minus of minus m which is equal to the 0. So here observe so minus 6m by 5 plus 1 and minus 2m by 5. These are the negative values. Among these two, most negative value is the minus 6m by 5 plus 1. So here we have to choose the most negative value. So that is the minus 6m by 5 plus 1 for the x2 column. So x2 column is calling as the key column and it is calling as the incoming vector. So x2 variable is enter into the basis. So x2 variable is enter into the basis. Next, to calculate the minimum ratio of xp divided by ck. So for the S1 row, xb value is the 8 and ck value is the 16.5. So 8 divided by 16.5 which is equal to the 2.5. And next to for the second row, for the A1 variable row, 6 divided by 6 by 5 which is equal to the 5. Next for the third row, so x1 variable row, 2 divided by 2.5 which is equal to the 5. So here minimum ratio is the 2.5 and is indicated by arrow. So S1 variable is outgoing variable and S1 is calling as the outgoing vector and it is calling as the key row. So here key row is the S1 row. So S1 variable is leaves from the basis. So next we have to identify the common element in the key row and key column. Here 16 by 5 is the common element. So key element is the 16 by 5. Next once again I have to construct the new simplex table by entering the incoming vector. So here x2 variable is incoming variable and s1 variable is outgoing variable. So we have to replace x2 with the s1. So enter the x2 variable in the new simplex table. So that is for the second iteration table. And its coefficient value is the cost coefficient value is the -3. So I have to write down the -3 in the CB column. So next once again I have to apply the following row operations to get the new simplex table. First row operation is the R1 new equal to the R1 volt divided by key element 16 by 5. So which is equal to the R1 volt into 5 by 16. So here R1 volt elements. First one is the 8. So 8 into 5 by 16 which is equal to the, so here 88 into 5 by 16. So 5 by 2 which is equal to the 2.5. Next to 0 divided by 16 by 5 which is equal to the 0. Next to 16 by 5 into 5 by 16 1. Next to 1 into 5 by 16 5 by 16. Next to 2 by 5 into 5 by 16. So which is the 1 by 8. Next to 0 into 5 by 16 0. Next row operation is the R2 new equal to R2 volt minus 6 by 5 into R1 new. So first write down the R2 volt elements. So next write down the R1 new elements and multiply with the 6 by 5 of the R1 new. Then R1 new elements will become the 3, 0, 6 by 5, 6 by 16, 6 by 40 and 0. Then I have to substitute R2 volt minus 6 by 5 into R1 new, which is equal to the 6 minus 3 which is equal to the 3 and 0 minus 0 0 and 6 by 5 minus 6 by 5 0 0 minus 6 by 16 minus 6 by 16. Next 2 by 5 minus 6 by 40 which is equal to the 1 by 4. Next 1 minus 0 1. Next row operation is R3 new equal to R3 volt minus 2 by 5 into R1 new. So write down the R3 volt elements. So next write down the R1 new elements. Then multiply with the 2 by 5. Then 2 by 5 into R1 new elements are the 1, 0, 2 by 5, 2 by 16, 2 by 40 and the 0. Then R3 volt minus 2 by 5 into R1 new is the 2 minus 1 which is equal to the 1 and 1 minus 0 1. 2 by 5 minus 2 by 5 0. 0 minus 2 by 16 minus 2 by 16 minus 1 by 5 minus 2 by 40 which is the minus 1 by 4 and 0 minus 0 which is equal to the 0. This is the new simplex table, that is the second iteration table. So here once again I have to determine the Zj minus Cj values. So Z1 minus C1 value is the 0. Z2 minus C2 equal to the 0. Z3 minus C3 equal to the 2m by 8 minus 5 by 8. Z4 minus C4 equal to the minus 2m by 8 plus 7 by 18. Z5 minus C5 equal to the minus 5. So here negative values are the minus 5 and minus 2m by 8 plus 7 by 18. So here I have to choose the most negative value is the minus 2m by 8 plus 7 by 18 because so big M. So M is the very large variable. So minus 2m by 8 plus 7 by 18 is the most negative value. So minus 2m by 8 plus 7 by 8 is value for the S2 column. So S2 column is the key column and calling as the incoming vector. So S2 variable is leaving from the basis. Next step is calculate the minimum ratio of XP divided by CK. So for the first row, that is the X2 variable row, XB value is the 5 by 2 and CK value is the 1 by 8. So 5 by 8 divided by 1 by 8 which is equal to the 5 by 2 into 8 which is equal to 20. Next for the second row, XB value is the 3 and Ck value is the 1 by 4. So 3 divided by 1 by 4, which is equal to the 3 into 4 equal to the 12. And next for the third row, x1 variable row, xb value is the 1 and Ck value is the negative. So if the value is 0 and negative, we are not considering that ratio. So we are not calculating the xb divided by Ck for the third row, that is the x1 variable row. So among all these values, minimum value is the 12. So minimum ratio is the 12 and indicated by the arrow. And here A1 is outgoing vector and it is calling as the key row. So here A1 row is the key row and A1 variable is leaving from the basis. So next we have to identify the common element in the key row as well as the key column. So here 1 by 4 is the common element, that is the key element is the 1 by 4. Next once again I have to construct the new simplex table by entering the incoming vector. And this is the new simplex table, that is for the third iteration table. So here Z4 minus C4 value in S2 column is the largest negative. So non-basic variable S2 is chosen to replace artificial variable A1 in the basis. So have to replace the S2 with the A1. So I have to write down the basis variables are the x2, s2, x1 and its cost coefficients values are the -3, 0 and -5. And next we have to remove the A1 variable column. So in this regard we are not representing this column in the new simplex table. So next we have to do the following row operations for the next iteration. First row operation is the R2 new equal to R2 old divided by 1 by 4. So which is equal to the R2 new equal to the R2 old into 4. So I have to modify the R2 new elements, which is the multiply with the 4. Then so here 3 into 4, so 12, 0 into 4, 0, 0 into 4, 0, minus 6 by 16 into 4, which is equal to the minus 6 by 4, and 1 by 4 into 4, which is equal to the 1. Next row operation is the R1 new equal to R1 old minus R3 new divided by 8. So write down the R1 old elements and write down the R2 new elements. And next operation is R2 new divided by 8, which is equal to the 3 by 2, 0, 0 minus 3 by 16 and 1 by 8. So next to do the row operation is R1 old minus R3 new divided by 8, which is equal to the 5 by 2 minus 3 by 2, which is equal to 1, and 0 minus 0, 0, 1 minus 0, 0, 5 by 16 minus of minus 3 by 16, which is equal to the 1 by 2, and next one is the 1 by 8 minus 1 by 8, which is equal to the 0. Next to row operation is the R3 new equal to R3 old plus R2 new divided by 4. So write down the R3 old elements. So next write down the R2 new elements and R2 divided by 4, which is equal to the 300 minus 6 by 16 and 1 by 4. So next to do the operation R3 old plus R2 new divided by 4, which is the 1 plus 3 equal to the 4, and 1 plus 0, 1, 0 plus 0, 0, minus 2 by 16 minus 6 by 16, which is equal to the minus 1 by 2, minus 1 by 4 plus 1 by 4, so which is equal to the 0. So this is the third iteration table. So once again I have to calculate the Zj minus Cj values. So first to Z1 minus C1, which is equal to the 0, and Z2 minus C2 equal to the 0, Z3 minus C3 equal to the 1, Z4 minus C4 equal to the 0. So here observe all the Zj minus Cj values are greater than or equal to the 0. So present solution is the optimal solution. So here all Zj minus Cj values are the greater than or equal to the 0 and artificial variables a1 and a2 have been removed from the basis. So optimal solution is arrived with x1 equal to the 4 and x2 equal to the 1 and s2 equal to the 12. And our objective function is maximize z equal to the minus 5x1 minus 3x2. Then substitute x1 value equal to the 4 and x2 value equal to the 1. Then maximize z equal to the minus 5 into 4 minus 3 into 1, which is equal to the minus 23. But original objective function is minimize z equal to 5x1 plus 3x2. So in this regard, once again I have to multiply with the minus 1. Then minimize z equal to the minus 1 into minus 23, which is equal to the 23. So value is the 23 is the answer. And thank you.